All right, everyone. I am here with Alison Gopnik. Alison is a professor at the University of California at Berkeley. Alison, welcome to the TWiML AI podcast.
Very happy to be here.
I'm really looking forward to our conversation. We will be focusing in on a presentation that you'll be delivering at this year's NeurIPS conference, focused on causal learning in children and how that relates to some of the things that we're doing in AI and deep learning. Before we dive into that, though, I'd love to have you share a little bit about your background. And you come at things from a psychology perspective. Tell us a little bit about your background and how you came to that field.
Yeah, so I actually started out my career in philosophy, and I'm still an affiliate in philosophy. So I have sort of three different hats at Berkeley. I'm in the psychology department, an affiliate in philosophy, and then part of the BEAR, the Berkeley AI Research Group. And the big question that I've really wanted to answer my whole career is this: how is it that we can know so much about the world around us from so little information? All we have are the photons in the back of our retinas and the disturbances of air at our ears. And yet people can figure out that the world is full of objects and people and thoughts and ideas and, quarks and black holes. How is that possible? And of course, that's the big problem of epistemology and philosophy, which is where I started out. How could you possibly do that? And it's the big problem of machine learning. It's the sort of central problem of machine learning. How could we get representations from data? And in a way, the way that the big problem, a way of putting this is we seem to have these very powerful, abstract, structured representations of the world around us that let us make great generalizations and predictions. And yet the data that we're getting doesn't seem to, is concrete and particular and doesn't seem to have those characteristics of being abstract and structured. So the question is, how do we get there, here from there? Well, very early in my career, I realized, look, the people who are doing that most effectively are actually young children. They're the ones who are going out into the world, taking what they see and hear and the actions they perform and figuring out what the world is like. So, if we want to answer that question, either as philosophers or as people in AI, the people we should look to, the people who are really solving that problem, are young children. And basically, that's what I've been doing for my whole career, is trying to figure out how is it that young children, 2, 3, 4 year olds who don't have PhDs in computer science, aren't philosophers, nevertheless seem to be solving these problems that have really stumped the smartest minds in philosophy and AI. And about 20 years ago, I started actually collaborating with people in both philosophy of science and in computer science to try and figure out, could we say something computationally? What kinds of representations and algorithms could the kids be using that let them learn as much as they do? And that's basically been the project ever since. And I think it's interesting that there's been, just in the past few years, there's been this real uh, uh, explosion of interest within AI in trying to look at development and look at children and use that as a clue to solve some of these really tough problems. And I think it's because so much of the new work has depended on the idea of designing systems that learn rather than trying to build things in the first place. And if you're interested in systems that learn, kids are a really wonderful, probably the best example we have of creatures that are really, really good at learning very accurately from small amounts of data. Um, so that's the big overarching picture about what I've done.
Fantastic. It sounds like you think about the problem of learning in children, broadly at the level of kind of these broad representations, but your talk at NeurIPS is focused on a particular aspect of that, and that is the way that children infer causal relationships and structure in the world. Tell us a little bit about your talk and your research in that area.
Yeah. So if you're asking this question, how do we get these big, abstract, powerful representations of the world? Um, one of the most important, not the only one, but certainly one of the most important kinds of ways we have of representing and thinking about the world is thinking about causality, thinking about what makes what happen. And the first line of work that I did with children was what's come to be called the theory, and that's the idea that children are building everyday theories of the world that are a lot like the way that scientists build theories of the world. And that's become, one of the most prevalent theories about how children solve this problem. They do something like build everyday theories of the world around them. But of course, then the question is, well, how do they do that, right? If you say that they're doing something like scientists, how do scientists build theories of the world around them? And and back in the aughts, there was a whole bunch of very exciting work showing that you could build causal pictures, causal representations of the world from data. And that's not the only thing scientists are doing. It's not the only thing involved in theory formation, but it's a really important thing in theory formation because if you have a causal model, if you have a theory, if you have a representation, then you can solve these out of distribution generalization problems. You can say, okay, well, uh, uh, if we do this to the vaccine, even if it's something we've never done before, we can predict what will happen because we have a causal model of how the vaccine works. Um, and the advantage of thinking about causal models, so they're an example of something that lets you generalize really broadly. And it isn't just letting you generalize about a specific area, like, the way that having a representation of everyday physics or a representation of the visual system could help you to generalize. Causality really covers everything. It covers the way that you interact with other people. It covers the way that objects work. It covers things that you've never seen before. So if you had a way of figuring out what makes what happen, if you had a way of figuring out causal structure, you'd have a really, really powerful tool for going out into the world and and solving new problems and making new predictions. One thing that's really important about causality, and a lot of people think of it as sort of being the thing that makes causality different from, say, just correlation of the sort that typical deep learning programs have done, is that causality lets you intervene, is the word that people use. It lets you decide what to do and think about what the consequences of that are. And causality lets you make counterfactual inferences. So it lets you, if I know that smoking um, causes lung cancer, for instance, if I think that that's right, then I'll know that even though smoking is correlated with yellow fingers, washing your fingers isn't going to help change the cancer rate, but not smoking, getting people to not smoke is going to change the cancer rate. And it also means that I can say, do some counterfactual. So I can say, well, look, if we had had not anti smoking programs earlier, we would have saved more people from cancer. So that ability to do interventions and counterfactuals is a very powerful aspect of causality and causal representations. And back in the aughts, people like Clark Gleamore and Peter Sperdes at CMU, and notably, probably most famously, Judea Pearl at UCLA, started developing these formal models for how those kind of causal how that kind those kind of causal representations could work computationally. So causal Bayes nets, probabilistic graphical models were the kinds of representations that they had. And back in the aughts, we started trying to see, are children doing something like inferring causal Bayes nets from data? And amazingly, much to everyone's surprise, it turns out that even if you're looking at 2, 3, and 4-year olds, they're really good at doing that. You can give them a pattern of data of conditional probabilities, and they'll pull out the right causal consequences from that data. So they seem to be doing something that looks like uh, very effective causal inference.
Going back to the theory, what were the alternatives to the theory before that theory, and how did you demonstrate that the theory was, um, was predictive and had merit?
Yeah, right. So that's a great question. And in fact, I think it should, people in ML and AI should be very familiar with what the alternatives were because they're the alternatives that we have in ML too. So one alternative, again, going back to really Plato and Aristotle, is look, it just looks as if we have all this abstract structure and representations. Really, it's just you've looked at a whole bunch of data and you pulled out the statistics of the data, and that's letting you make predictions. And that was one thing that the sort of what's sometimes called the empiricist option was, okay, maybe it's not that children have these abstract representations, maybe they're just following the data. And it just looks like they have the abstract representations because they have a whole lot of data and a whole lot of observations. And then the other option which again is very active in AI now, is, well, look, maybe they aren't actually learning the representations. Maybe they're just built in. So work that's being done in AI now suggests that you might have built-in uh, constraints, inductive constraints that are like assumptions about how the world works, assumptions about how physics work, or assumptions about how people work. And if you just build those in the first place, then you can help to solve the problem. So those were the two options that were and still are on the table. And I think those of us who actually look at young children learning, there are probably elements of both of those that are right, but it doesn't look like either of those is what's happening, because from the time we can test, and this is where the great methodological and experimental advances in developmental psychology kick in, even very little babies already seem to have these abstract, powerful representations of the world. That's very different from what a previous generation thought about babies. Um, but at the same time, even 3 and 4 year olds, this is work that we did back in the 80s, are really changing what they think about the world based on their experience. So they seem to be have abstract representations and be learning and changing those representations from the time they're very little. And theory of mind, for example, which is something that people are thinking about in AI as well, that ability to understand what's going on in someone else's mind, that was the work that we did back in the 80s that I think really clearly showed that children have this succession of everyday of everyday theories of the world. And then in the more recent work about causal inference, what we could show is not just that they will have an abstract theory and then another one based on the data, but we can actually say something about what those look like, what the representations look like, and how the representations change.
Does the theory imply that children are taking an active role in kind of recognizing that a theory is a theory and testing the bounds of that theory and experimentation?
Yeah, exactly. So that's the thing that is the new work that we're really doing now. So we showed
Okay.
over an extended period that children could do this. They could get statistics. They could infer causal structure. And you might wonder, how on earth could you do this with like 2 year olds, right? I mean, if you
Uh-huh.
asked most grown-ups, what does this pattern of conditional dependencies indicate a causal chain or a common effect, they would be not know what you were talking about. And the way we did it is we have a little machines. One of them is called the Blicket detector that you'll see in my talk. It's a little box that lights up when you put things on it, plays music sometimes and doesn't other times. So it's a new causal system. And the kids' challenge is to figure out how it works, figure out which things are blickets. Well, blickets will make it go, which things are blickets, and then they have to make it go themselves. So without
Okay.
actually asking about causal structure, we can see what kinds of inferences they're making, and we can
Mm.
control what kind of data we give them. So we can give them different patterns of data, and then we can see what they do. We can see what kinds of inferences they make. And as I said, to a remarkable degree, the kids are making the right kinds of inferences. If they were little Bayesian hypothesis testers, again, to get back to the theory, give them two hypotheses and they're picking the ones with the best posterior probability. But the big
Mhm.
question is, so that's really impressive. But then we still have this question about how are they doing that? What's happening that's letting
Yeah.
them solve that problem? Because of course, the big issue with Bayesian reasoning and with probabilistic generative models in general is if they're interesting at all, the search space is enormous. So if you think about even a Bayesnet with 4 or 5 causes, you very quickly have a very very big space of possibilities. And the question is, how do you limit that? How do you search through that space? How do you solve that problem? An idea that we've had and a lot of people in AI have had now is that active learning, to get back to your question, active learning, experimentation, that's the way that scientists solve that problem. They are
Mm.
not just, you're not just, stuck in your mainframe with data pouring over you.
Right.
You can actually decide which kinds of data you want depending on what kind of hypothesis you're testing. And for causal work, again, because of this intervention quality of causation, you can specify pretty clearly, here's the kind of experiment you should do, here's what you should do, here's how you should wiggle x to see if y works. And if you think about little kids, I mean, like, that's their entire life, right?
Right.
I just This is a kind of nice, it's a kind of nice convergence. I just spent a, a sabbatical at Mila in Montreal, where Yoshua
Okay.
Bengio and his colleagues are doing fantastic work just about this question about causal inference and causal models. And at the same time, I was visiting my 1-year-old grandson. And if you watch my 1-year-old grandson, basically all he does is do experiments. I mean,
Mhm.
he will occasionally eat if his mom gives him some food, and other than that, what he's doing constantly is doing experiments, and what all the rest of us are doing is trying to keep him from killing himself by doing experiments. Uh, and it's funny, we just sort of take for granted, "Oh, okay, look, I'm looking at this 1-year-old and look what he does. He takes the spoon and then he bangs it on the pot and then he turns the pot over and then he sees if he can stick the spoon in the light socket and so on and so forth." We just take that for granted, but why would they be doing that, right? I mean, that's a lot of physical energy going on to just go out and try things in the world. But if you think of them as being these active causal inference engines, that's exactly what they should be doing. And what we're doing now is in collaboration with some people at Mila and at Berkeley, um, and actually at Google DeepMind as well. What we've done is to set up these environments in which you can find out about causal structure by doing experiments. We have our kind of virtual version of our Blicket detector, and what we can do is see what do kids do when you just let them loose in this kind of environment, and how does that compare to various kinds of causal learning algorithms you might have. And if you think about it, like a classic RL algorithm, for example, is not going to do the kinds of things that are the best experiments, because the classic RL algorithm is just going to try and find the outcome and maximize it. And what you need for experiments is to try lots of different things, change what you do based on what happened before. So, uh, but some of the things, again, like my colleagues, Deepak Pathak and Pulkit Agrawal and others coming out of Berkeley, have these curiosity-based algorithms that seem to be closer to what the kids are doing. And I think if you kind of combine the curiosity-based idea, the idea that what you're trying to do is get a system that will make predictions and frustrate them and explore, and the causal models idea, that could be a very powerful mechanism for solving some of these search problems.
To what degree does your work begin to um, kind of articulate, explore the structure of the complexity of causal relationships that children are able to deal with at various ages? And what does that tell us about our ML models?
Yeah, so the first pass, both with Bayesnets and with our work, was just pretty simple causal relationships. So here's one variable and another variable, and does variable X cause variable Y? And you can see the experiments you do to try and find that out. And then what Pearl and Gleamore and colleagues had done was to look at more complicated things like, is it a causal chain, or is it a common effect structure or common cause structure? Uh, but starting in the late aughts, we started collaborating with people like the cognitive scientist Tom Griffiths, who's at Princeton, Chris Lucas, who was a student of mine who is now in Edinburgh, to try and see if we could also make inferences about more abstract features of causal systems. So, for instance, could I infer not just, is this Blicket detector, did this block make the detector go or not, but is the detector deterministic or stochastic? Or does the detector work with a conjunctive logic? You need two things to make it go in combination. Or does it have a disjunctive logic? Each cause is separate. And what we've shown is that kids are quite good at, even again, 3 and 4-year-olds are quite good at making inferences about those more abstract features of the system as well. And to get back to machine learning, the more abstract your representations are, the more powerful your generalizations are going to be. So the kids seem to be quite good at even making those more abstract inferences. And something that's really interesting is that the kids are actually better at doing that than adults are. So, uh, uh, well, here's the thing, and this is another point about children and childhood in general. So if you give the adults a structure that's really common, that they have a strong prior for, then they're
Mm.
good at making the inference. But how about if
Mhm.
it's something that's kind of weird and unusual? So it's an abstract feature that isn't as obvious and you don't have as strong a prior for. When you do that, the kids are actually better than the adults. And
Mm.
in a sense, the kids' lack of knowledge, lack of previous knowledge is really an advantage when you want to explore the space more widely. And I think that leads to another big point that I've made that I'll be making in my talk, which is that actually just it gets back to my 1-year-old, just being a kid, just the fact that you have this period of childhood before adulthood, that in and of itself may be something that humans use to solve this problem. And the argument that I've made is, again, think about that search problem. One of the reasons the search problem is so challenging is because there are always these explore exploit trade-offs, right? So
Yeah.
one of the things that we learned at the very beginning of computer science was that explore exploit trade-offs are a bear and there isn't any simple or optimal way of resolving them. But one
Mhm.
idea that people often have is, okay, when you look at the actual algorithms that are trying to deal with explore exploit tensions, is start out exploring, and in particular start out with these very wide, high temperature, bouncy, noisy kinds of searches that get through a whole bunch of the space. And and then once you've done that, narrow in and exploit. And the idea is that that keeps you from, getting stuck in local optima. It keeps you from settling on a particular option too quickly. And what I've argued is you could think about human life history, as they call it in biology, human development as being evolution's way of. So one of the ideas is often a simulated annealing kind of uh, uh, idea. So you start out looking really widely, and then you really with a really high temperature, and then you cool off. And and my slogan is that childhood is evolution's way of solving the explore exploit tension and doing simulated annealing. So if you sort of say, who looks like they're bouncy and random and noisy and trying lots of things that are not very effective versus who looks like they're narrowing in, using a lot of their prior knowledge to do something effectively, you'll see that first, that's what a 1-year-old looks like, and as opposed to what an adult looks like. So part of the idea is that if we actually built in a developmental sequence, we sort of let AIs have be children for a while, that might we might also get some clues about how to learn more effectively. And this kind of trade-off that you see where the children need a lot of care, they need a lot of people around them looking after them, but that gives them this chance to go out and explore. That might be a trade-off that's relevant for AI as well. And I should say, in some of the other things that I'm going to talk about, one thing that we've been doing is looking at how children are using experimentation and exploration to try and solve these problems.
So one thought that brings to mind for me is, in some ways, could you say that the natural machine learning cycle kind of resembles this childhood adulthood, in a sense that training is kind of like childhood, and inference, once the model is kind of built and fixed, then that's kind of adulthood?
Something like that, I think, is right. Yeah, I think the idea is that you have a period of learning, and then you have a period of actually using what you've learned to go out and make inferences. Um, but the kind of learning that the children are doing seems to be much more wide ranging than the kind of learning that a typical machine learning system is doing. And something that I think is really interesting is when you actually look at the practicalities and talk to people about, well, how do you solve these explore exploit problems? Annealing shows up again and again, and often in multiple cycles where you'll, do heat things up, cool things down, heat things up, cool things down. But there isn't a kind of general theory about how to do that, as far as I can tell, or about why that works. And again, looking at the kids might give us some clues about, how does annealing work in the wild when you see it in children. One of the things that I think is really cool about this idea is if you think about explore exploit trade-offs, things that look like bugs from the exploit perspective might actually be features from the explore perspective. So, for instance, having a system that's noisy, that has a lot of variability, um, is not good if what you want is to make inferences and act effectively, but it is good if what you want is to be able to learn as much as possible. So many of these things about kids that have seemed like defects, like the fact that they're curious all the time, that they're kind of unpredictable, that they are variable, that they're noisy, those might actually be advantages from the perspective of learning. And I think we don't have a good theoretical account of how that all works, and thinking about the kids could help.
What would you say are the closest ways that we're approximating that in the machine learning world?
People like uh, Joshua Bengio and his colleagues and others are trying to now, and I think this is going to be the wave of the future, is to try and design hybrid systems that have some of the power of the that can use some of the power of machine learning, but then can also have some of the structure and generalization of a causal system. Um, so Joshua has these flow nets that are trying to do that. So they're trying to add a layer of further structure on top of a kind of classic machine learning system. And RL is interesting from this perspective too, because you could argue that, and people have argued that reinforcement learning in the psychological sense is like the most primitive form of causal learning, as opposed to just picking out correlations. What happens in reinforcement learning is that you do make an intervention and you see what the outcomes are. And it's important that you're actively going out and making interventions and seeing outcomes. But typically in RL, what you're the outcome of that isn't a model as much as just the fact that you're more likely to make those inferences or those policies later on. So something like model based RL ends up looking a lot like causal inference. It ends up looking a lot like causal structure. And that might be a relevant, that feels like that's a relevant um, outcome. But I think it's important that the objective functions for a system like that would have to be things like information gain or like knowledge or like curiosity, rather than being things like how well you're scoring on some measure. And there's really elegant work in our labs and others that show, for instance, that if you look at the kids playing around, they seem to be acting in a way that will get them information. That information gain seems to be sort of an objective function that describes what it is that they're doing.
What's an example of that?
Well, there's beautiful work by my colleague Celeste Kidd, and she looked at really young babies, like 10-month-olds. And what they did was they showed the babies different sequences of events that had different amounts of information in the technical information theoretic sense. And what they discovered was that there was this kind of sweet spot, and they just measured how long the babies looked at each of these events. And they discovered there was this sort of sweet spot. If something was too random, too far removed from where you were now, the babies wouldn't look. But they also wouldn't look at things that didn't give them very much new information. There was this kind of sweet spot of just where the information gain was going to really help you to make progress. And the babies looked the most at those events. And we've been thinking about that too. One of the problems with using information gain, this is something that comes up in a lot of these curiosity based RL kind of algorithms, is what's called the TV problem. The problem is if you just use technical information gain, then if you just put someone in front of a random a TV with random static at it, you're getting lots of
Mm.
information in the information theoretic point, but you're not getting anything that's actually going to be very useful. So I
Right.
think one of the real interesting frontiers is this balance between noise and structure, right? So the kids are
Mhm.
noisy, but they're not just completely noisy. They're not just acting like random agents. They're doing things that make sense given the kinds of problems they're trying to solve, the kinds of causal structures that they're trying to infer. And how you get that balance between introducing noisiness and variability and then also having interventions and experiments that are relevant to the problems you're trying to solve, that's something that kids seem to be really remarkably good at doing, and we don't quite know how to characterize that computationally.
Mm, mm. I had cut you off to ask a question earlier, and you were about to mention some additional points from your talk. What
Y-
were those?
Yeah, so what we've been doing now, so one thing that we've been doing is looking at how children are using active learning to figure out the causal structure of the world in these online environments. Another thing that we're doing is trying to see if I mentioned that we'd done work showing that children could get these more abstract what are sometimes called over hypotheses about causal structure. But one thing that we're doing now is trying to see if kids can do things like actually decide what the right causal variables are. So a big problem. So it's easy to say, okay, look, I'll tell you, here's variable X and here's variable Y, and then you can see whether they're dependent and see if there's a causal relationship between them. But how do you decide which variables to look at in the first place? And this is a big problem for ML as well, where it turns out that, in the classic adversarial examples for something like ImageNet, it turns out, well, wait a minute. No, the system is actually not even dividing up the world in the right way. It's paying attention to, fine details of the texture instead of paying attention to the objects. Um, and it might look as if it's making the right kinds of inferences, but it isn't really, because it just hasn't divided up the world in a way that makes sense from the perspective of different variables. Um, if you're a scientist, there's all sorts of classic examples like, it turns out that if you're looking at the relationship between cholesterol and heart disease, oh, there's actually two different kinds of cholesterol. One of them makes heart disease more likely, one of them doesn't. So if you didn't have the right measures, if you just looked at cholesterol overall, you wouldn't see the relationship. And then it turns out that you can. Uh, and it turns out that kids are actually very good. We have some really beautiful experiments where kids are actually good at picking out, oh, okay, this is the variable, this is the object, or this is the property that is the one that I should be looking at for purposes of trying to do causal inference. So they're simultaneous. Yeah. So this is my brilliant graduate student, Marielle Gadou. So what we do is we set up a situation where the kids have to figure out their little Shelly the turtle wants to grow cactuses, and he likes some cactuses. He likes the ones with round things on them, but not the spiky ones. And we're trying to decide, how can we help him grow his cactuses? And there's two different things we can do. We could put the seeds in different colored flower pots, or we could have different colored watering cans that are watering the seeds. And we're trying to figure out, how do we make sure that Shelley gets the cactuses that he does? So we've set up, here's these two potential variables. It could be the watering cans, it could be the pots. And what we can show is that if we show children that the watering cans make a difference and the pots don't, and now we give them a new case, this is a new cactus, a new watering can, a new pot, they'll say, okay, the watering can is the thing. I hope I got that right. The watering can is the thing I should be paying attention to. I should be playing with that watering can. I should be changing it. We should be doing things to that watering can, because I've already figured out that the pot really isn't relevant to these differences. So in philosophy, they talk about this as causality being difference making. The causal thing is the thing that makes a difference. And the kids already seem to be saying, okay, which things in my world are the things that make a difference? Which are the things that I can control and change and make a difference? And again, if you think about an AI system, if it was paying attention to think about RL, part of the problem with RL is it's just paying attention to everything in the image, right? And if it could say, oh no, these are the things that I should be varying, these are the things that if you think about like the classic example where you see a robot being trained with RL and it's doing all this ridiculous, stupid stuff that isn't going to make any impact at all, before it kind of stumbles on the thing that might work. If you could start out having that robot say, oh, okay, I know these are the things that are going to make a difference and these things aren't, it would be much better off. And if it could learn that, that would be even better.
Does your research um, venture into the role of biases learned by children in the process of their exploration?
Yeah, one of the things that I mentioned before was about the fact that children aren't just using these causal inferences to draw conclusions about, Blicket machines. They're using them a lot to draw inferences about other people. And actually, something that we haven't published yet, we're just in the middle of doing it. For example, um, suppose kids see that there's a bunch of kids who are playing together, and kids who have, a particular kind of funny glasses are being welcomed into the group, and kids who have a funny hat are being shunned, for instance. So they just would be seeing those patterns. Are they going to conclude that there's a difference between the people who have the glasses and the hats. Even if, I mean, that's a nice example of variable selection, right? Kids start out not thinking that this difference is going to be important, but if they see that people are being treated differently, they might very well end up concluding, and in fact, we have some evidence that they do conclude that those people are those are different groups. Those are people who should be treated differently, for example. So I think it's quite plausible that part of what's happening is that kids are paying attention to these social differences, and then they end up having various kinds of biases as a result. And it's an interesting question about would it seems plausible that an AI might very well reproduce that, and we might be worried about how we could counter that both for the children and for the AIs.
So, what are the main takeaways that you want to leave the folks that are hearing your talk at the Causal Inference and Machine Learning workshop?
So I think there's two. One of them is this may be a little preaching to the choir, is that causal inference is really important. It's a really powerful technique. Causal representations give us lots of advantages, and and we've sort of made some progress computationally on causal inferences and representations, and that's exactly the technique we'd need to solve some of the limitations of our current systems. But then, in a way, the even more important idea is that looking at little kids, which is not something that typically people in AI have done, it feels like, oh, wait a minute, the world of people who are sitting in little chairs and playing with 3 year olds is completely different from the world of computer scientists. And I think it's kind of wonderful that computer scientists have realized, oh, wait a minute, these little kids who we weren't paying any attention to, we thought they were just,
Hmm.
kind of, I don't know, um, uh, mushy stuff that wasn't like what we do in
Yeah.
AI. That those are that those are really, those kids might really have the clue to designing new systems. I think that's the really big point that I want to make, and I think back and forth by looking at kids who are such great learners, we can figure out how to make more effective AI. But also by looking at AI, we can figure out what's going on in those kids' brains that makes them such effective learners. I think that's a
Hmm.
really, really promising, exciting uh, uh, line of research, and one that we're starting to do, and I hope we'll continue to do.
That's awesome. So, AI researchers, go play with your kids.
Exactly. Yeah. I mean, I and I think this might be an example as well where the diversity issues are really relevant, right? So,
Hmm.
I think part of the reason, to be frank, why kids haven't played a bigger role in AI is because kids are kind of girl stuff, right? There are things that people who are off raising families are paying a lot of
Hmm.
attention to, and the people who were doing AI and the people who are raising the families haven't necessarily been the same people. And I think it's a
Hmm.
kind of tribute to the way that we have a much wider, more diverse group of people being involved in AI, including more women, more people who are raising families. That's a nice example where that actually turns out to contribute to something that's really basic to the science.
Yeah. Yeah. Awesome. Awesome. Well, Allison, thanks so much for joining us and sharing a bit about your talk and what you've been up to on the research front.
That's
Very cool
great.
stuff.
Well, thanks for having me.